Tiny fluctuations in the density of the early universe, differences of only about 1 part in 100,000, are ultimately responsible for every galaxy, every star, and every planet that exists today. Right after the Big Bang, the universe was a hot, dense plasma, a fluid of photons, electrons, and atomic nuclei all tightly coupled together. In that soup, gravity was already at work, trying to pull slightly denser regions into even denser clumps. But there was a competing force. Radiation pressure, photons kept slamming into charged particles, pushing back against gravity. The result was a kind of cosmic tug-of-war that created sound waves in the early universe called baryon acoustic oscillations, literal pressure waves rippling through primordial matter and light. Where matter was slightly denser, gravity pulled harder, compressing that region which heated the plasma and intensified the photon pressure. That pressure then pushed matter back outward, creating expanding shells of higher and lower density. Importantly, these waves didn't erase the original fluctuations. They just sculpted them into a characteristic pattern of preferred scales. Like certain notes being louder in a piece of music, we can still see the frozen imprint of those waves today in the cosmic microwave background, the afterglow of the Big Bang, as tiny temperature variations at the level of tens of microkelvin. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons and helium nuclei, forming neutral atoms. This event is called recombination. With the electrons bound into atoms, photons suddenly stopped scattering so often and streamed freely through space. The universe became transparent. The pressure support from trapped radiation dropped away for normal matter, but the dark matter, which had never interacted with light in the first place, had already been quietly clumping this entire time, influenced only by gravity. Dark matter acts like an invisible scaffold. In regions where it was slightly denser, its own gravity pulled more dark matter in, forming growing concentrations called dark matter halos. Because dark matter doesn't collide or radiate, it couldn't get rid of energy by glowing. Instead, it passed through itself and settled only through gravity, building an intricate, three-dimensional cosmic web of filaments and nodes over tens to hundreds of millions of light-years. Once the universe was transparent, ordinary gas, mostly hydrogen and helium, began to fall into these dark matter potential wells, like fog collecting in the valleys of an unseen mountain range. As gas accumulated in a halo, it was shock-heated to millions of degrees Kelvin, then slowly radiated away that energy as light, cooling and sinking deeper into the halo's center. This cooling allowed the gas to become denser, triggering gravitational collapse on smaller scales. Within a few 100 million years after the Big Bang, at redshifts of around 20 to 10, the first stars ignited. These were likely massive, short-lived giants, many tens or even hundreds of times the mass of our Sun, born in tiny protogalaxies, just a fraction of the Milky Way's eventual size. Each protogalaxy was a small, chaotic star-forming region embedded in its larger dark matter halo. From minuscule ripples in density to the first blazing protogalaxies, gravity and cooling gas turned statistical fluctuations into luminous structure. But once the first stars lit up the cosmos, they also started to fight back against gravity, reshaping and sometimes even tearing apart the very galaxies that birthed them.